For my talk today, I'm going to be drawing on the contributions of an amazing bunch of students, JRFs, and collaborators that I've had the pleasure to work with over the years, many of whom have crossed paths with ATREE or are here in this room. There's Atul Joshi, whoa, that's interesting. Yadagiri, Hari, Siddharth, Chenga, Manaswi, and Rasika, and also my wonderful collaborators, Dr. Jayashree Ratnam, Dr. Jagdish Krishnaswamy from ATREE, who used to be at ATREE, and Srinivas Vaidyanathan and Ravi Balla from Ferrell. Okay, so right, one central tenet that has sort of pervaded ecological thinking for more than a century now is the idea of a climax community or climax vegetation as depicted in this Whittaker biome classification figure, right? And essentially what it says is for a given combination of rainfall and temperature, you're likely to see one particular kind of vegetation type or a climax vegetation type. So in really wet areas, you're going to get tropical forests, and in cold, dry areas, cold deserts, and so on. And we know this holds true for the most part, right? But there are some notable exceptions, and one of them being these montane forest grassland mosaics. So here we have a system where under the same climate, you have two distinct vegetation types, grasslands and forests, coexisting with abrupt boundaries between them. And these formations are not just restricted to the Western Ghats. We find them all across the globe. You can see them in Malawi, in Sri Lanka, in Brazil, Bolivia, Madagascar, and so on, right? So they tend to be very restricted where they occur, but we find them in a lot of places. And for the longest time, because people were wearing the Clemensian lens and looking at it as a climax community, people thought that these were originally forests, but at some point they've been degraded because of human activity or because of fire, right? But is that actually the case? So are they natural or are they in fact anthropogenic artifacts? So this is work from Professor Sukumar's group in the Upper Nilgiris, where they took sediment cores from these mosaics, and they dated them. And because the grasses and the trees have different isotopic signatures, you can figure out, what is the relative abundance of grass and trees in these systems. And so that's what the graph on the left shows. If you go back on the y-axis is the proportion of trees and grasses. And this goes back 40,000 years. And we know that even though the ratio of trees to grasses has changed, both trees and grasses have persisted in the system for over 40,000 years, right? So they've persisted for at least 40,000 years, and they were prevalent before human presence in the area. And there's a lot of evidence from across the globe, both isotopic and palynological from pollen, which suggests that many of these mosaics are in fact ancient. They predate human settlements, suggesting very strongly that they're in fact natural ecosystems and they're not the result of human activities, right? So this raises two interesting questions for me. One is, how do they come about in the first place, right? How do these mosaics form? And the second one is, what actually maintains them? I don't know the answer to the first question, so I'm just going to skirt it, and we're just going to look at what actually maintains these mosaics at the current time, right? So what maintains forest grassland mosaics? And again, people have been thinking about this for a long time, and they've been debating this for nearly a century right now. And people have come up with many different hypotheses. There's microclimate, which is a very prevalent one, saying there's differences in the microclimate, which actually, particularly the occurrence of frost, which allows these mosaics to persist. Others argue for soil, saying there are inherent differences in the soils, and which is why in some areas you find grassland, other areas you find forests. There's a role for fire, saying fire has this positive feedback loop that maintains the grasslands, and fire doesn't get into the forests, and so that's why it's fire that maintains the mosaics, and herbivory also, right? So there are many different reasons proposed. And if you go back in the literature and look at it, we'll see statements like this. Hence, frost occurrence probably does not provide a satisfactory explanation for the restriction of sholas to the depressions and the grasslands to the exposed surfaces. The assumptions that grasslands are steady-state vegetations maintained by edaphic factors or soil holds good. With no conclusive evidence for the frost hypothesis, the fire hypothesis has gained favor, and fire has an important role in maintaining these grasslands. And also, although all these statements have been made, there were actually no tests or experimental tests of these different hypotheses. At least that was till Atul Joshi, who was sitting there, came along. So some of you might have heard already the next few minutes of my talk, because I'm going to be delving deeply into Atul's work. So this is the question we set out to ask in the Upper Nilgiris. What is it that actually maintains these mosaics, right? So just brief history. Atul went to the India office and looked through past communications. So this is what Ooty looked like, in 1857. As you can clearly see, it was predominantly grassland with Shola forest in there. And of course, because the colonial foresters looked at this, like I said, from that climax viewpoint, they assumed that these are degraded habitats, and so they went ahead and started planting trees, right? So that's St. Stephen's Church, and as you can see, that's how the landscape has changed from being an open grassland to now a wooded area. And I think they planted more than 40 or maybe more species. Many of them didn't hold, but a few of them, and particularly one, went out of control, and that's Acacia mearnsii wattle. You can see that bright green patch, there's a Shola patch, and all the rest, that dirty green, used to be grasslands, but it's now wattle, right? So the extent of the invasion is actually pretty intense, and we've lost a huge amount of the grasslands in the last few decades. So, what limits tree establishment in grasslands? So we looked at it, saying, where is the demographic bottleneck? Is it at the seed to seedling transition, is the seedling to sapling transition, or the sapling to adult transition, right? Where exactly is this bottleneck? And what is it that prevents trees from actually establishing in these grasslands? So the first thing is, do soils and microclimate influence this pattern? Because people have argued that it's soil, others have argued that it's microclimate. And so this was the experiment that was carried out. We took soils from both the grassland and from the forest, and we planted seeds of the species in both these soils. And then we placed these trays either in the forest microclimate or in the grassland microclimate. What do the results show? And this was well replicated and so on. So this is the germination, right, results. And as you can see, there's pretty much no difference between grassland soil and Shola soil. The dark bars are the invasive acacia, and the light bars are the native species. Right, no effect of soil type on germination success. And in fact, if we look, there's more seedlings germinating in the grassland than in the forest, right? Suggesting that, it's not that, that's not the bottleneck. And here's the other thing, the germination success of the invasive acacia is 3 times greater. So we know that soils is not a bottleneck, right? So soils is not a bottleneck here. And in fact, the microclimate for the grasslands seems even better for the seedlings, at least at the germination stage, than within the forest. So what is it then? Is it the transition from the seedlings to the saplings? And we just followed these seedlings over time and looked at their survival. And this is what the survival looks like over the winter, right? The blue lines are the native species, and the red lines are the invasive plants. On the left is the grassland microhabitat. On the right is the sholas within the forest. And you'll see that what happens in the grassland is, by the end of the winter, all the native seedlings are dead. But the invasive survives, whereas inside the forest, both the native and the invasive species are about to survive. So there's something about the microclimate. It's not at the germination stage, but it happens over the winter, so strongly suggesting that something that happens over the winter is what's limiting these trees from establishing in these patches, right? So drastic overwinter mortality of native seedlings, but higher survival in the Shola patches. And if you look at the temperatures, that if you go across a 10-meter boundary from inside the forest to the grassland, these are the minimum temperatures that you record over the winter, right? Within the forest patches, temperatures only go down to 4 or 5 degrees, but 10 meters away, temperatures go down to -5. So just over a 10-meter gradient, you're seeing a 7 to 10 degree change in temperature from inside the forest to the grassland. Again, strongly suggesting that it's low winter temperatures that actually limit tree establishment. So we went ahead and actually tested this. We did an experiment, Atul did the experiment, where we tried to warm the seedlings. So if it's low temperatures that limit it, then if you warm the seedlings, then their survival should go up, right? So we had all these species. It was a warming experiment with 5 native species and 1 invasive. And essentially what was done was we placed these thermal blankets over these seedlings at night so that it'll actually maintain the temperatures and not let it go below freezing, and then take them out in the morning. And this was done through the growing season, right? And if you see the temperatures in the control, you have lots of nights of frost and freezing, whereas in our experimental warming, it's only 2 nights that it actually went below freezing because we were unable to put the blankets up in time. So what do these results show us? Again, on the left, the control is the same as before. By the end of the winter, most of the native seedlings had died. The invasive had survived. Whereas if we warm it, survival of even the native species goes up considerably. There's about 40 to 50% of them surviving across the winter. But if you look at the invasive, it's going up to 90%. So all of this strongly suggests that there's significantly greater survival when protected from freezing temperatures, suggesting that maybe it is frost that's actually limiting tree establishment here. But the overwinter survival of acacias is going to be much, much more, right? So these results suggest that long-term low nighttime temperatures are actually what limits the tree establishment in this system. And so, which means that future warming is likely to going to facilitate the establishment of trees in these grasslands, which is bad for the grasslands. But the bigger problem is the invasive species are going to be facilitated much, much more than the native species. So it's going to cause a much greater problem with the invasion than already exists, right? So this is a problem. How do we deal with it? But I'm just going to change tacks here and just talk about what are the effects that these invasive species are having in these systems, right? So this is work by Manasvi, who also I believe is sitting there. So we looked at what are the community level consequences. What are these invasions doing to plant diversity in this system, right? And there are many other invasives that I'm not going to talk about much. We have gorse, we have ulex, and we also have some plantations. The green lines are the species richness in the grasslands, and the colored lines, the red lines, are species richness within an adjacent patch that has been invaded or is a plantation. As you can see, there's a significant reduction, almost half in some cases, of species richness. So these invasive species are having a very huge negative effect on the richness of these grasslands. They're also homogenizing plant communities. This is just an ordination plot for the different sites. Points that are closer together are more similar in composition. And that whole big box on the right is the grasslands, and everything else on the left are either plantations or invaded patches. As you can see, plantations or invaded patches tend to be more homogeneous. They're more similar in species composition than the grasslands, which are very diverse. So we're reducing diversity, and we're changing species composition to make it more homogeneous, right? What else are they doing? Are they having any ecosystem level consequences? Right, again, work from Manasvi, we looked at what they're doing to the carbon cycle, and the bottom line is the grassland doesn't have much soil carbon. This is across depths. The green line is the Shola, but these plantations now have intermediate levels of soil carbon. So there's actually more soil carbon in these invaded patches, which, if you think from the lens of climate mitigation, you'll think it's good, but it's not always good. Right? There are many cases it comes at a cost of biodiversity and everything else. And this is associated with greater inputs as well as lowered soil respiration. So if you look at soil respiration, that's how much CO2 is coming out of the soils. Grasslands have very high, 0.57 grams per meter square per hour, and Shola and wattle patches is much lower, 0.5. Right, so there's more inputs coming out of carbon, there's less losses, and which is why carbon is going up in these invaded patches. What about nitrogen? All of these invasive species are nitrogen fixers, so there's actually more nitrogen in the system too, so they're making it more fertile. There's more total nitrogen, And there's also more inorganic N availability. So if you look, that line on the top, there's more inorganic N, and inorganic N is mobile, right? So when it rains, what happens? All that inorganic N tends to flow off. This is work done with ATREE and Feral. And what these graphs show is the amount of nitrate in stream water from catchments that are dominated by grasslands on the left, wattle-dominated catchments, 2 of them in the middle, and the Shola-dominated catchment on the right. And the grassland and the Shola-dominated catchments behave the same, but when you have invasive species, you're seeing a lot of nitrogen flowing out, which is bad because it causes eutrophication downstream and it affects water quality and so on and so forth, right? And they've also altered fire regimes. This is work by Rasika. This is a burnt patch, and this is a DBNR. You don't need to worry about it, but the dark areas are areas that have burnt with higher intensity than the lighter areas. And it turns out that many of the dark areas are areas that are actually been invaded by one of these 3 species, Scotch broom, wattle, or gorse. And in fact, gorse is the worst in terms of changing the fire regime, but even wattle patches burn with very high intensity. So they're changing the carbon cycle, they're changing the nitrogen cycle, they're changing the hydrological cycle, and they're changing the fire regime. So woody plant invasion of these grasslands has reduced native plant diversity. It has homogenized plant species community composition. It has altered ecosystem carbon, nitrogen, and hydrological cycles, and it has altered fire regimes, right? So there's a huge bunch of changes going on as a result of these invasions. So what does the future hold? We don't know the answer to this question. We've started looking at many things. We don't know how the invasive patches are going to respond. But what we've looked at are the grasslands, and we've experimentally warmed these grasslands using these open top chambers. They're like mini greenhouses that you can put there, and we've monitored carbon flux from these patches. This is work done by Yadugiri. And as you can see, the dark lines are the warmed patches, and the lighter gray lines are from the controls. And warming by 1.5 degrees, which is what's predicted, is going to almost lead to a doubling of carbon going back into the atmosphere, which has huge implications for the global carbon cycle. But what happens in the invaded patches, we don't know yet because we haven't manipulated it. But hopefully, we'll give you the answer to that in a few years. Right. So increased future temperatures are likely to exacerbate woody encroachment, leading to further loss of these grasslands, including many rare and endemic species, further alter ecosystem carbon, nutrient, and hydrological cycles, and impact fire regimes. So what do? I don't know, it depends on how you're approaching it. I think everybody has a different point of view. It's quite a highly debated sort of field. Do we go ahead and restore it? If we're going to restore it, how do we do it? I approach it from the view of a grassland ecologist, and I think these are some of the last remaining grasslands. And my point of view is that restoration of these grasslands is a priority. Not everybody thinks so, but I'm happy to take this offline and argue about it. I think I'll stop. Maybe I've gone too much. Yeah, thank you.
Thank you, Mahesh. We have time for one question. One sharp question.
I should have gone longer than that. Sorry.
What are the differences in biodiversity? What are the human use differences between patches which are natural grassland and grasslands which have invasive species? Could you comment on that? Thank you.
Yeah, human use, I can't comment. I'm sure there are people in ATREE who are better qualified to do it because most of this work was done in areas where human presence is low. It's Forest Department, land and national park, so there's human presence. It's currently low, not was low in the past. But yeah, diversity is significantly reduced from about 9 species per meter square to about 5 or less in some cases. So there's a huge loss of local native plant species diversity at local scales. For all of the invasive, wattle, Scotch broom, gorse, everything, all of them are reducing diversity to a huge extent.